Now, today we are going to be arguing about how light is both a wave and a particle. So, Sambhav here will be proving that light is a wave, and I will be trying to prove that it is a particle. And we'll use
All
experimental
right.
results to achieve the result, to achieve the goal. So, there's this experiment that was conducted in the 19th century that proved that light is a wave. So what they did, they made light pass through a very small hole, right? And what
Yes.
happened was interference took place. And interference only takes place in waves. So with me, I have an animation and a projection of what it was like,
So here the light generator, Kushagra.
right? So this is the light generator, and these are the two slits. Okay. This
Hey.
is the copper sulfate screen. A copper sulfate screen records the photons that hit it basically. So I'll just switch on the light generator and you'll see something very fascinating happen. So as you can see in these regions, the waves kind of intersect each other, right? And this is the process we call as interference. So in light waves, what happens is there are two types of interferences. There's one destructive interference and constructive interference. If you can look at this black mark on the screen, and just before that we have this recorder thingy, electric field recorder. So what's happening is destructive interference. The waves pass each other, and because of their motion, and what you need for this is they need to have the same wavelength and frequency, right? If they do have the same frequency and they are congruent, but they have a difference of 180 degrees, what we see is destructive interference, such as in this case. Over here, destructive interference takes place. All these black marks you see, these are destructive interference marks. And over here, we see constructive interference. This takes place when two waves of the same frequency intersect and interfere with each other. So their amplitudes double up, right? So this is what you see over there. If you can see this graph of the electric field, the black mark is not moving at all because it's basically zero, while the white mark is going up and down in a sine curve. So this is basically the concept of interference, and this is what Thomas Jung proved through his experiment. So because interference takes only in waves, we can confirm that light is a wave. Now I'll share my screen and prove on how it is not a wave but a particle, right?
Now, I have a doubt in
Okay.
this part of a wave, of proving a wave interference. Now,
Yes.
if light was a particle, what would happen as it went through the double slit?
Well, nothing would happen, right? It would just go through. I mean, when a particle goes through something, it just travels in a straight line, right?
Yeah, so it would have just traveled in a straight line, rectilinear propagation style.
Yes. But if you looked at the screen, if you looked at the copper sulfate screen, you would have noticed that there are some marks. I'll just share my screen again.
Yeah, yeah, I got that.
Yeah.
Since that's what proves that it's a wave, or at least the point towards that.
Yes.
Okay, I got it. Thank you.
And if it was a particle also, this wouldn't have worked out properly. Because if you know about this scientist, the Great Cat Experiment, can you name the scientist who performed the Great Cat Experiment?
If you tell, you mean Schrodinger's cat?
Yes. So this is kind of a
Yeah,
Schrodinger
Schrodinger.
proof through this. So if a particle goes through a space so small, right, then so basically what he proved was you can't know the momentum and the position with 100% accuracy.
Yeah,
So if it goes through a slit so small, a photon, then we know its position because it's like really confined, and light speed is constant, so we kind of know the momentum as well. But this shouldn't work out. So that's another reason why this phenomenon takes place. Now I'll share my screen again for another experiment, the photoelectric experiment phenomena, and prove that light is nothing but a particle. So this is the photoelectric effect, right? So before this, I'll give you some basic insight about light itself. So light, according to this theory, this is Maxwell's theory, consists of photons, right?
Yeah.
And the energy of a photon is directly proportional to its frequency. This is the Planck's formula. Energy equals Planck's constant into frequency. So, and then there's intensity. So intensity of a light determines the number of photons it has. Okay, make sense?
Yeah. Yeah.
So now what happens in the photoelectric effect is when so Einstein and Max Planck discovered that when light hits a metal, some amount of electricity is generated. Now this was like really fascinating in the 19th century. So do you know about the metallic structure? Like, do you know about the electronic configuration of metals?
Uh, yeah, it's like, okay, I don't know it by heart, but it's like, uh, 1s square,
No, in metals, like not
two
the element, but the metal as a whole. So this is what happens. There's random nucleuses everywhere, positively charged nuclei, and they have a sea of electrons around them, right? So
yeah,
basically, there's electrons everywhere.
uh-huh.
This is also why metals are such good electricity conductors, and this is also why they are such good heat conductors. So, anyways, when light strikes an electron, a photon strikes an electron, after like if the photon has enough energy, which is determined by the frequency. So, if the photon has enough energy, the electron is freed, right? The electron gains energy and it's freed. So, that is a threshold frequency. Threshold frequency is the minimum frequency required to free electrons of a specific metal, of course. Make sense?
Yeah, yeah, it does.
This is the apparatus for the photoelectric effect, or kind of like an experiment in this case. So what we'll do is we are using sodium as our metal, right? We can use other metals as well. And we'll show current versus light intensity and electron energy versus light frequency, because the frequency is the amount of energy in a photon. That's what the frequency determines. And when a photon hits an electron, the electron gains energy, right? Conservation of energy or momentum for that matter. And current is the number of electrons passing a point per second. And it's based off light intensity in this case, because intensity is how many electrons are ejected per second. I mean, how many photons are ejected per second. So I'll just start this simulation by increasing the intensity. Yes, we have good intensity, but we don't have a good frequency, right? So
Yeah,
this, the light has not passed the threshold frequency. The energy per
yeah,
photon is too low for the electrons to be free.
infrared basically.
Yes. So as we increase the frequency, you can see that the energy in the electrons release has increased significantly. So here's the graph as visible, electron energy versus light frequency. You can see the graph, and what happens if the intensity changes? So I'm going to slightly decrease the intensity. So as we decrease the intensity, the number of electrons and hence the current has changed, right? You can kind of see a measurement over there for the current. I'll change the
Yeah,
frequency. The current increases instantly. So this was a really fascinating phenomenon that proved that light is
uh-huh.
a particle. So this was discovered by Einstein and Max Planck, and Einstein also got his Nobel Prize for this discovery. So we have discussed the photoelectric effect, and so in the end, is light a wave or a particle?
Honestly, in my opinion, I feel like it contains both the properties of a wave and particle, but I think in practically, it should be considered to be, uh, as a whole, a wave, but to a level, it should be like a particle, because it's quite, whenever it comes to the mass of the entirety of light, like as a beam, it's a wave. But
Yes.
when you're taking it as an individual product, it should be a particle.
According to me, it's more of a particle, though. I
It
think.
depends on what kind of
Yeah,
optics you're
yeah,
talking about.
yeah. Practically, it should be a particle, because when we consider light in like equations, and yeah, but like when it comes to like equations and you know discussing light, you usually take it in the form of a particle moving at the speed of light, not exactly like a wave, you know?
Yes. So light is, I think, one of the confusing things. And if you look at electrons, the same thing happens with electrons. Like instead of both of these experiments, if you put alpha particles or electrons, you'll get the same results. And the best part about Thomas Young's experiment is even if you fire up like 1 electron per minute or 1 photon per minute, you'll get the exact same result, even though it's so-called random.
Yeah. That's interesting.
Yeah. So Jung proved that light is a wave, while Einstein and Max Planck proved that it has lumps of energy, photons, and so it turns out it's both, right? And it turns out not only light, but everything is both an object and a wave. So if you
To an
remember, we talked
extent.
about, yeah, if you remember, we talked about Planck's equation, right? Over here, E equals hf.
Yeah.
There, h is Planck's constant. H is a constant, yeah. So energy equals Planck's constant into frequency, right? And energy kind of depends on the
Yeah.
mass always, right? So
Yeah.
if you think about it that way, our energy as humans or any macro objects can also be converted and thought about as waves, but they'll have like a kind of like a big frequency, a very big frequency, and hence a very small wavelength, a wavelength so small that it doesn't really matter.
Yeah. Yeah. Okay. Yeah.
Because if the wavelength was big, then we would be like constantly fluctuating, right? But our
Yeah.
wavelength is like so small it doesn't matter.
It's negligible.
Yes, it's negligible. So Vamsi, would you like to sum up the session?
Sure. So what we basically learned from this session is that photons, or light in general, when it's shot through a double slit, we find that it interferes, which is a property only found within waves. So we can say that light has the property of a wave. Yet light also interacts with metals in a way that a particle would. So we can say that it's also a particle. But in actuality, light contains both these properties, and this property is called particle-wave duality.
Yes. That's all for today, guys. Any doubts or any FAQs, please feel free to ask me.
I think I understood quite well. I'm not sure about Shubham though. I think he understood well as well then.
Yeah.